Could this discovery mark the downfall of Einstein's theory of relativity? For years, dark energy has been regarded as a mysterious force, one that pushes against gravity and accelerates the expansion of the universe. But new evidence suggests that this cosmic engine may have been evolving in ways that defy our standard cosmological model. And that's just the beginning. In a stunning development, the James Webb Space Telescope has done it again. Its powerful instruments have revealed yet another ancient galaxy, one that, by all accounts, shouldn't even exist. How is it possible that just 2 billion years after the Big Bang, a galaxy could already be significantly more massive than our own Milky Way? Today, we'll break down exactly what Webb uncovered and how astronomers are grappling with these seemingly impossible findings. So stick around to the end as we dive into the full story behind these puzzling discoveries, where theory clashes with reality in truly mind-bending ways. According to our well-established models of cosmic evolution, the early universe, shortly after the Big Bang, was home only to tiny, fledgling galaxies. These were far smaller and less massive than the grand spiral giants we see today. That made sense to us. Galaxy formation takes time, and back then, the universe simply didn't have enough ordinary matter to build something as massive as the Milky Way. Or so we believed. Then came the James Webb Space Telescope, and with it, a cascade of surprises. Time and again, Webb has uncovered objects that our theories said shouldn't exist. Most famously, the so-called universe breakers, colossal galaxies as massive as the Milky Way, appearing just a few 100 million years after the Big Bang. Their existence alone shook the foundations of cosmology. But the surprises haven't stopped there. Now, Webb has spotted something even more astonishing, an object so massive and unexpected, it overshadows previous discoveries and leaves astronomers with yet another cosmic conundrum. More precisely, this discovery involves a galaxy dubbed the Big Wheel, a massive spiral galaxy that existed just 2 billion years after the Big Bang and was already 5 times more massive than today's Milky Way. Interestingly, scientists weren't originally searching for such extraordinary galaxies. They were using the James Webb Space Telescope to study a distant quasar and its active supermassive black hole. But during their analysis, led by Wen Wang from the University of Milan Bicocca, researchers spotted something remarkable in the lower left corner of the image, a colossal spiral galaxy with clearly defined arms. After measuring its redshift, they realized the light had traveled approximately 11.88 billion years to reach us, meaning this galaxy formed when the universe was only about 15% of its current age. The galaxy was later named Big Wheel and its discovery published in Nature Astronomy. According to the findings, this cosmic giant spans about 100,000 light-years in diameter, making it as large as our Milky Way. How did the Big Wheel galaxy grow so rapidly? At the same time, scientists analyzing data from the James Webb Space Telescope were able to uncover details about its rotational behavior, and the results are astonishing. The galaxy spins at an incredibly high speed. While this rotation aligns with the Tully-Fisher relation, a well-known correlation between a spiral galaxy's rotation speed and its luminosity, which helps estimate its distance, what's truly remarkable is what this implies. The Big Wheel is one of the most star-rich galaxies ever discovered from the early universe. Even more surprising, its structure and properties closely resemble those of the largest and most developed spiral galaxies we see today. But according to our current understanding, that shouldn't be possible. After all, our models indicate that spiral galaxies typically grow slowly over extended periods. This growth usually happens either through the steady inflow of gas from surrounding space or by merging with smaller star clusters. But such encounters aren't without consequences. These interactions tend to disturb the delicate structure of spiral galaxies, often leaving them with distorted, chaotic forms. That's why it's especially puzzling that the Big Wheel managed to reach such a massive size in a relatively short time, all while maintaining its classic spiral shape. What's more baffling is that it doesn't appear to possess any unusually rapid growth mechanism. However, its growth rate isn't unusually fast, it's actually comparable to that of other galaxies of a similar age. But how is that possible? How can the existence of the Big Wheel be explained? Researchers believe the key lies in its cosmic neighborhood. The Big Wheel isn't located in just any region of space, it's in an area where the density of galaxies is about 10 times higher than average. And according to astronomers, that's precisely what makes the difference. In such a densely packed environment, the Big Wheel likely experienced several galactic mergers. But these weren't the violent, disruptive collisions we often see. Instead, the mergers were surprisingly gentle, so gentle, in fact, that the galaxy was able to retain its spiral shape. On top of that, gas from the surrounding area likely flowed into the galaxy in a way that matched its rotation, allowing the spiral disk to expand quickly without becoming distorted. In other words, the Big Wheel formed in the right place at the right time. And the same can be said for the researchers who discovered it, because finding the Big Wheel was, in itself, incredibly unlikely. According to our models, the chance of detecting a galaxy like this during a survey is less than 2%. Scientists likely only spotted the Big Wheel because it was resting in an unusually dense region of space, quite different from typical cosmic environments. Does this mean our standard model is flawed? While the rapid growth of early galaxies raises concerns among experts on a smaller scale, there's also a bigger problem that challenges the broader picture. In short, new research indicates that a fundamental foundation of our cosmological understanding is being seriously questioned, and our standard model might soon become outdated. Let's explore why. To understand what's going on, we first need to remember that the universe isn't a fixed, unchanging structure. Instead, it has been continuously expanding since its beginning about 13.8 billion years ago. Back in the 1990s, astronomers were surprised to discover that, contrary to expectations, the expansion of the universe wasn't slowing down, it was actually speeding up. In theory, gravity from all the matter in the universe should have acted like a brake, slowing this expansion. But since that wasn't happening, scientists realized there must be some other force pushing the universe to expand faster. This mysterious force was named dark energy. However, dark energy remains hypothetical, its existence hasn't been experimentally confirmed, and it's still surrounded by many unanswered questions. According to the standard cosmological model, dark energy's density is constant across time and space, meaning it acts like a fixed cosmological constant. At least, that's what we believed until recently. New evidence has been piling up, suggesting that this cosmological constant might not be so constant after all. One clue comes from the so-called Hubble tension, which refers to the fact that the universe appears to be expanding faster than theoretical models predict. Additionally, research from last year revealed that dark energy may be varying more than expected, challenging the standard model based on Einstein's relativity. This puzzling discovery has gained fresh momentum thanks to the latest data from the DESI experiment in Arizona, where astronomers have mapped over 15 million galaxies and quasars to better understand dark energy's true nature. When combined with data from other sources like supernovae, cosmic background radiation, and gravitational lenses, the deviations from the standard model show a significance ranging between 2.4 and 4.2 sigma. Mustafa Ishaq Bushaki from the University of Texas at Dallas suggests that this indicates we are steadily approaching a critical tipping point. Meanwhile, Kasadri Nadather from the University of Portsmouth notes, we now have multiple datasets all pointing in the same direction. The evidence points toward a changing nature of dark energy, with a level of confidence higher than ever before. But what does this actually imply? Simply put, experts say these findings deepen the doubts about the standard model, indicating that what was thought to be a constant might not be constant after all. As DESI co-spokesperson Alexei Lode-Harnett puts it, what we are witnessing is profoundly intriguing. We may be on the verge of a groundbreaking discovery about dark energy and the fundamental nature of our universe, a discovery that could also mean that Einstein's theory of relativity does not fully apply in every respect. DESI spokesperson Will Purcell from the University of Waterloo explains that it's becoming increasingly clear we may need to revise our standard model. But are there any theories that can explain the unexpected behavior of dark energy? Actually, yes, some propose a concept called the phantom crossing of this mysterious force.